There is a feeling that haunts many physicists, a sense that no matter how successful our theories become, no matter how precisely they predict experimental outcomes, something remains unsatisfied, incomplete, as if we have grasped important truths without fully understanding what they mean or how they fit into a complete picture of reality. This feeling of incompleteness is particularly acute in quantum mechanics, the theory I helped develop and have defended throughout my career. People often ask me whether quantum mechanics is complete, whether it tells us everything there is to know about atomic reality, or whether there might be some deeper theory waiting to be discovered. My answer is subtle and perhaps surprising. Quantum mechanics may be complete in one sense while physics itself necessarily remains incomplete in another, deeper sense. Understanding why physics feels incomplete, and what kind of incompleteness this is, requires us to think carefully about what we mean by completeness, and what we can reasonably expect from physical theories. Let me begin with my own experience of this feeling of incompleteness. When I developed my model of the atom in 1913, I achieved something remarkable. I could calculate the energy levels of hydrogen with extraordinary precision. I could predict the wavelengths of spectral lines that had been measured by spectroscopists. The agreement between theory and experiment was stunning, one of those rare moments when abstract calculation matches concrete observation almost perfectly. And yet, even in my moment of triumph, I felt a deep dissatisfaction. I had imposed quantum rules on electron orbits without understanding where these rules came from. I had postulated that electrons could only occupy certain discrete energy levels, that they made instantaneous jumps between levels, that they did not radiate while in stationary states. These postulates worked, but I did not know why they were true. I had answers without understanding, success without completeness. This feeling intensified as quantum mechanics developed through the 1920s. Werner Heisenberg developed matrix mechanics, Erwin Schrödinger developed wave mechanics, and we discovered that these two apparently different formulations were mathematically equivalent. We had a rigorous mathematical framework that could make precise predictions about atomic phenomena. We could calculate probabilities for measurement outcomes, predict energy levels, understand chemical bonding, explain countless experimental results. By any practical measure, quantum mechanics was extraordinarily successful. And yet, the feeling of incompleteness persisted. What did the wave function really represent? Why did measurement cause the wave function to collapse? Where was the boundary between the quantum system and the classical measuring apparatus? What was really happening when an electron existed in a superposition of different positions? We could calculate with the formalism, but we could not agree on what the formalism meant, what kind of reality it described, how to think about what was actually occurring in the atomic world when we were not measuring it. Albert Einstein articulated this feeling of incompleteness most forcefully. He believed that a complete physical theory should describe reality as it is, independent of observation, with all properties having definite values at all times. Quantum mechanics, he argued, did not do this. It only gave probabilities for measurement outcomes. It said that particles did not have definite properties between measurements. It relied on the mysterious process of measurement to collapse superpositions into definite states. To Einstein, this meant quantum mechanics was incomplete. There must be hidden variables, deeper properties not described by the wave function, that determine what happens in individual events. The wave function merely reflected our ignorance of these deeper realities. I disagreed with Einstein about whether quantum mechanics was incomplete in his sense, but I understood his dissatisfaction. The theory did not provide the kind of complete description that classical physics had led us to expect. It did not tell us what was really happening between measurements. It required us to use both quantum and classical concepts without fully explaining how they related. It left fundamental questions unanswered or, more troubling, suggested that some questions we naturally wanted to ask had no answers. My response to this was to argue that Einstein's notion of completeness was inappropriate for quantum mechanics. He wanted a theory that described an observer-independent reality with all properties defined at all times. But quantum mechanics showed us that nature does not have this character at the atomic level. Properties are not all simultaneously definite. Measurement plays an irreducible role in bringing properties into definite existence. The quantum world is fundamentally different from the classical world, and demanding that quantum mechanics provide classical completeness is demanding something that nature herself does not offer. In this sense, quantum mechanics might be complete. It might give us all the information that exists about quantum systems. The wave function might be the most complete description possible, not because we have failed to discover deeper variables, but because no such variables exist. The feeling of incompleteness might arise not from deficiency in the theory but from our inappropriate expectations about what completeness should mean. And yet, I confess that even with this understanding, the feeling of incompleteness does not entirely disappear. There is something unsatisfying about saying that the wave function gives complete information, while also saying that many properties do not have definite values, that measurement plays a special role we cannot fully explain within quantum mechanics, that we must use classical concepts to describe experimental arrangements even though everything is ultimately made of quantum systems. This is not the kind of unified, transparent completeness that physics has traditionally sought. Let me explain why I think physics necessarily feels incomplete, and why this is not a flaw but a feature of how we relate to nature through physical theories. The first reason is that physical theories are always formulated in language and concepts that we develop based on our experience, but our experience is limited to a tiny corner of physical reality. We evolved to interact with macroscopic objects at moderate speeds and energies. Our intuitions, our concepts, our language all reflect this evolutionary history. When we try to describe the atomic world or relativistic speeds or cosmological scales, we are using tools adapted for a different domain. Quantum mechanics feels incomplete partly because we are trying to describe quantum phenomena using concepts like particle and wave that were developed for classical phenomena. These concepts do not fit quantum reality perfectly. We must use both concepts in complementary ways, and we can never achieve a single unified classical picture of what is happening. This is not because quantum mechanics is deficient but because the concepts we naturally use are inadequate for the domain we are trying to describe. No matter how complete the mathematical formalism becomes, the translation into ordinary language and intuitive concepts will always feel strained and incomplete. The second reason physics feels incomplete is that we cannot escape the perspective of being observers within the universe we are trying to describe. In principle, a complete description of physical reality would include everything, including ourselves and our measuring instruments and our consciousness. But we cannot step outside this reality to achieve a view from nowhere. We are always inside, always limited to certain perspectives, always dependent on the concepts and tools available to us within the system. This necessary limitation means that our descriptions must always have a certain incompleteness, a recognition that we are part of what we are trying to describe. This is particularly acute in quantum mechanics because of the role of measurement. We must describe measuring apparatus classically, using definite properties, because that is how we communicate what we observe. But measuring apparatus are made of atoms, which are quantum systems. There is an unavoidable circularity here. We use classical descriptions for some things and quantum descriptions for others, with measurement bridging between them, but we cannot give a complete description of measurement itself purely within quantum mechanics without losing the ability to communicate definite results. Does this mean quantum mechanics is incomplete? In a sense, yes, because it cannot fully account for the measurement process from within its own framework. But this incompleteness may be unavoidable given our position as observers within the reality we are describing. It may reflect not a deficiency in quantum mechanics but a fundamental limit on what any physical theory can achieve when formulated by observers who are part of what is being described. The third reason physics feels incomplete is that we keep discovering that our theories apply only within limited domains. Newtonian mechanics, which once seemed like a complete description of motion, turned out to be an approximation valid only at speeds much less than light speed and for objects much larger than atoms. We discovered relativity for high speeds and quantum mechanics for small scales. Even quantum mechanics as we currently have it does not include gravity in a fully consistent way. We expect that at extremely high energies or small distances, some more fundamental theory is needed. This pattern suggests that completeness is always provisional. Any theory that seems complete today may turn out to be an approximation tomorrow when we explore new regimes. The feeling of incompleteness may be a healthy awareness that our current theories, however successful, have boundaries beyond which they cease to apply or need modification. Physics feels incomplete because it is incomplete in this sense, always limited to certain domains, always potentially subject to revision or replacement. But there is a fourth and deeper reason why physics feels incomplete, one that I have thought about extensively. Physics necessarily abstracts from the full richness of reality to focus on certain aspects that can be measured, quantified, and predicted. We isolate systems, idealize conditions, focus on properties that can be expressed mathematically. This is essential for doing physics, but it means we are always dealing with models and approximations rather than reality in its full complexity. Consider an electron. Quantum mechanics gives us a wave function that describes the electron's quantum state. We can calculate probabilities for any measurement we might perform. In one sense, this is complete information about the electron as a quantum object. But is this the same as understanding the electron completely? The electron has a history, exists in relationships with other particles, participates in the electromagnetic field, has properties we have not measured and perhaps cannot measure. The wave function captures certain predictive information, but does it capture everything about what it is like to be this particular electron at this particular moment? I am not suggesting we need some mystical or non-physical understanding. I am pointing out that physical theories necessarily abstract, selecting certain features as relevant and ignoring others. The selection is guided by what we want to predict and control, by what we can measure, by what can be expressed mathematically. This is good methodology, but it means our theories are always incomplete in the sense of not capturing everything about physical reality, only those aspects we have chosen to describe. There is also the question of understanding versus prediction. Quantum mechanics allows us to predict experimental outcomes with remarkable precision, but does it help us understand what is really happening? I can calculate the probability that an electron will be detected at a certain location. But do I understand why it appeared there rather than somewhere else with non-zero probability? The theory gives the probability, which is complete predictive information, but it does not provide the kind of causal explanation that would feel fully satisfying. Some physicists have tried to escape this feeling of incompleteness by proposing alternative interpretations or extensions of quantum mechanics. The many worlds interpretation says that all possible measurement outcomes occur in different branches of reality, giving a kind of deterministic completeness at the cost of multiplying universes beyond anything we can observe. The pilot wave theory gives particles definite positions at all times, providing classical completeness at the cost of introducing elaborate non-local hidden variables. These approaches trade one kind of incompleteness for another, solving some problems while creating others. I have always felt that the Copenhagen interpretation, which emphasizes complementarity and the role of measurement, is honest about the kind of completeness quantum mechanics can provide. It does not pretend to give us a complete classical picture of reality independent of observation. It acknowledges that different experimental contexts reveal complementary aspects that cannot be unified into a single consistent picture. It accepts that measurement plays an essential role that cannot be fully reduced to or explained by quantum mechanics alone. This is not satisfying in a classical sense, but it may be the most complete understanding possible given the actual structure of quantum reality and our position as observers within that reality. The feeling of incompleteness in physics is also connected to the incompleteness of mathematics itself. Kurt Gödel proved that any sufficiently powerful formal system contains true statements that cannot be proven within the system. There are inherent limits to what can be achieved by formalization. Physics, to the extent it relies on mathematical formalism, may face analogous limits. There may be truths about physical reality that cannot be captured within any formal physical theory, aspects that necessarily escape mathematical description. Moreover, physics depends on concepts like space, time, causality, substance, property, and many others that we take as primitive but do not fully understand. We use these concepts to formulate theories, but the theories do not explain the concepts themselves. Where do these concepts come from? Why do they work? Are they ultimately grounded in something more fundamental, or are they irreducible features of how we must think about the world? This conceptual incompleteness runs through all of physics. I have spent much of my career arguing that we should accept certain kinds of incompleteness rather than demanding a completeness that nature does not offer. We should accept that position and momentum cannot both be precise, that wave and particle properties cannot be observed simultaneously, that measurement plays an irreducible role, that some questions have no answers because they presuppose inappropriate concepts. This acceptance is not defeat but mature understanding of what kind of knowledge is possible. And yet, accepting incompleteness does not mean abandoning the search for deeper understanding. Physics continues to make progress, to unify previously separate phenomena, to find deeper principles underlying surface regularities. Quantum mechanics and relativity were both revolutionary advances that revealed new depths in our understanding of nature. Perhaps future theories will go deeper still, revealing structures we cannot currently imagine. But I suspect that no matter how deep we go, the feeling of incompleteness will remain. It will remain because we are finite beings trying to understand an infinite reality, because we are observers trying to describe a universe that includes us, because our concepts and language are adapted for one domain but must stretch to cover all domains, because abstraction necessarily leaves out aspects of concrete reality, because prediction is not the same as understanding, because mathematical formalism cannot capture everything. The feeling of incompleteness in physics is not a temporary problem to be solved by a better theory. It is a permanent feature of the human condition as knowers embedded in a reality we try to understand. Physics gives us extraordinary power to predict and control. Remarkable insights into the structure of nature, beautiful mathematical patterns that govern phenomena. But it does not give us the kind of absolute, transparent, complete understanding that we might desire. And recognizing this, accepting the necessary incompleteness of physics while still pursuing deeper understanding wherever possible, is part of the wisdom that comes from a lifetime of engaging with the deepest problems in physics. So when people ask me whether quantum mechanics is complete, I say yes in one sense, no in others. Yes, it may give us all the predictive information that exists about quantum systems. Yes, demanding more information than the wave function provides may be demanding something nature does not have. But no, it does not answer all our questions about what is really happening. No, it does not unify quantum and classical descriptions in a fully satisfying way. No, it does not eliminate the feeling that something remains unexplained, mysterious, incomplete. And this feeling, uncomfortable as it may be, keeps physics alive as an active enterprise of discovery rather than a closed system of final answers. The incompleteness drives us forward, makes us question our assumptions, pushes us to find deeper principles and broader frameworks. If physics ever felt complete, if we had all the answers and no remaining puzzles, that would be the death of physics as a living science. The feeling of incompleteness is the feeling of being engaged with something greater than ourselves, something that continually reveals new depths, something that will never be exhausted by our theories no matter how successful they become. This is why physics feels incomplete, and why it must necessarily feel that way. Not because we have failed, but because the enterprise of understanding nature is itself inherently incomplete, always partial, always provisional, always reaching for something beyond what we currently grasp. And this incompleteness is not something to lament but something to embrace as the condition of genuine inquiry into the nature of reality.